Hello everyone, welcome to the tutorial on how to evaluate performance metrics of a RAG pipeline. Today we will firstly discuss what are the performance metrics, then we will talk about what are the different types of retrieval metrics, and then we'll talk about the generation metrics. Then we will implement all these metrics to evaluate a RAG-based chatbot, which I have built in my previous tutorial, and then we will see some improvement strategies to improve these performance metrics. So let's get started. So when we build a RAG system, an initial challenge comes out whether the output of the RAG system is of high quality or not. The response produced by it is factually correct and coherent or not, and the generated response should not have a lot of noise. And our RAG system should not generate responses which are harmful or toxic, and most importantly, our RAG system should perform well. So here, performance metrics comes into the picture. Performance metrics are quantitative measures used to evaluate the effectiveness, accuracy, and efficiency of the RAG system. So now let's talk about some retrieval metrics. The precision metrics is a measure of how accurately the retrieved context matches the user query. Recall metric is used to evaluate the ability to retrieve all relevant context for a user query. Relevance metrics is used to assess the relevance of the retrieved context to the user query. Entity recall metric is used to determine the ability to recall relevant entities within the context. The noise robustness metric is used to test the ability of the system to handle noise or irrelevant inputs. Now let's talk about generation metrics. Faithfulness score is a measure of how accurate and reliable generated answer is. Answer relevance is used to evaluate the relevance of generated answer to the user's query. Information integration metric is used to assess the ability to integrate and present information cohesively. Counterfactual robustness metric is used to test the robustness of the system against the counterfactual or contradictory or counterfactual queries. Negative rejection metric is used to measure the system ability to reject and handle negative or inappropriate queries. And lastly, latency metric is used to measure the response time of the system from receiving a query to delivering an answer. Let's implement performance metrics and deep dive into these metrics to evaluate our RAG pipeline. So let's start by importing necessary libraries: NumPy for numerical operation, time for measuring latency, cosine similarity and TF-ID vectorizer from sklearn for calculating relevance scores, sentence BLU from NLTK for BLU score calculation, ROC scorer from ROC score for ROC score calculation, Spacey for natural language processing tasks like entity extraction, Torch, BERT tokenizer, and BERT for sequence classification from Transformer for evaluating the faithfulness of the generated answer using BERT. Then load models like English NLP model from Spacey and a BERT tokenizer and model for sequence classification. So before proceeding to the performance metrics, let's see what is query, ground truth, get response, and vector store that we will be going to pass into the function as an argument for calculating metrics. So queries is a list of queries to be answered by the chatbot. Ground truth is the list of dictionaries containing the expected context and answer for the queries. Get response function is used to generate a response for a given query using the RAG pipeline. And vector store is the storage for vectorized text representation used for retrieving relevant context based on the similarity searches. This too I have already discussed in my previous tutorial, so you can watch that. Now coming to the precision and recall, as discussed, precision measures how accurately the retrieved context and match the user query. And it is calculated as a ratio of true positives, that is relevant context retrieved, to the number of total context retrieved. Now coming to the recall. Recall evaluates the ability to retrieve all relevant context for the user query. It is calculated as a ratio of true positive to the total number of relevant context. To find precision recall, let's define a function. Firstly, define a helper function, that is convert to list, to convert a nested list of strings into a flat list of string for easier processing. And then define a recall function and precision recall function, which takes two arguments, retrieved and ground truth. Convert these arguments into list and then into a set and store it as a retrieved set and ground truth set. Then we will calculate true positives by finding the intersection of the retrieved set and ground truth set. The intersection operation returns a set containing elements that are present in both retrieved set and ground truth set. Now finally, calculates the precision. Precision is defined as the number of true positives divided by the total number of retrieved context. If the retrieved set is empty, precision is set to 0 to avoid division by 0. Similarly, we will calculate the recall. Recall is defined as the number of true positives divided by the total number of relevant context, that is ground truth context. If ground truth set is empty, the recall is set to 0 to avoid division by 0. Now coming to the relevance, to calculate relevance, cosine similarity and TF-IDF, that is term frequency inverse document frequency, are used to score the relevance of retrieved context. Now let's define the relevance score function, which takes two arguments, retrieved context and user query. TF-IDF vectorization is applied to both the user query and retrieved context. The cosine similarity measures the angle between the vector representation and providing a relevance scores between 0 and 1. Now coming to the entity recall, the method called entity recall is used to extract using the entity extraction using species name entity recognition. Let's define entity recall function, which takes two arguments, retrieved context and user query. So the relevant entities, that is product, color, target, audience, these are the examples. There are many relevant entities can be fetched, which are extracted from both the user query and retrieved context. Entity recall is calculated as a ratio of true positives, that is entities correctly recalled, to the number of entities in the query. Now coming to the noise robustness, method to calculate the noise robustness is by introducing noise into the user query by randomly removing characters. Let's define the noise robustness function and pass two arguments, user query and noise level, and set a default value of noise level as 0.1 or a 10%. Now convert the query string into a space separated string of its character. This is done to ensure that the query is treated as a sequence of characters for the noise introduction process. Now creates a new string noise query by iterating over each character in the modified query string. For each character, a random number between 0 and 1 is generated using np.random.rand function. If this random number is generated, then noise level 0.1 is by default. The character is included in the noise query. If the random number is less than or equal to the noise level, the character is replaced with an empty string, effectively removing it. This process introduces noise by randomly removing characters from the query based on the specified noise level. Finally, it returns the noise query, which is the original query with some characters removed randomly based on the noise level. A noisy version of the query is generated and the relevance of the retrieved context is measured to assess the chatbot's robustness. Now coming to the faithfulness, it is measured using BERT for sequence classification. The generated answer and ground truth are input to BERT, and faithfulness score is derived from the model's output logis. So let's define a function named check faithfulness that takes two arguments, generated answer and a ground truth. Now using a tokenizer, that is BERT tokenizer, that is initialized earlier, to encode both the generated answer and ground truth into input tensor suitable for the model. The return tensor equals to pt argument specifies that the output should be in PyTorch tensor format. Now create a tensor containing a single label 1, indicating that the generated answer and ground truth are expected to be similar. The unsqueeze method adds an extra dimension to make the tensor shape compatible with the batch processing with a batch size of 1. Now pass the tokenized input and label to the model, that is a BERT model initialized earlier. To obtain the output, the model performs a forward pass with the input and labels. Now extract the loss and logist, which are raw model output scores, from the model's output. The output indexing assumes that the first two elements of the output tuples are the loss and logist and respectively. Now coming to the answer relevance, it is measured using the BLU score, which compares the overlap of n grams between the generated answer and the ground truth. Let's define a function as a BLU score that takes two arguments, generated answer and a ground truth. Now split the ground truth string into a list of words using the split method and wraps this list into another list. The resulting differences is a list of lists, which is the format expected by the BLU score function. Each inner list represents a reference sentence. Now split the generated answer string into a list of words using the split method. The resulting candidate is a single list of words representing the generated answer. Finally, calculate the BLU score by comparing the candidate list of words to the reference list of lists. The sentence BLU function from the NLTK translate BLU score module computes the BLU score, which is measure how closely the generated answer matches the reference answer. Now coming to the information integration, it is a measure by a ROG, recall-oriented understudy for a distinct evaluation. This is a score to determine the quality of information integration. ROG1 and ROG-L scores are calculated by comparing the generated answer to the ground truth, focusing on the overlap of unigrams and longest common subsequence, respectively. And let's discuss a function. Let's define a function named as a ROG score that takes two arguments, generated answer and ground truth. It initializes a ROG score object from the ROG scorer module to calculate ROG1 and ROG-L scores. The use stemmer is equals to true argument indicates that stemming would be applied to the words in the text, which means words will be reduced to their root forms. That, for example, if there is a word running, then it will become run. Now using the scorer object to compute the ROG score by comparing the generated answer and the ground truth. The result is stored in the score dictionary, which contains the ROG1 and ROG-L score, and finally returns the F1 score, a measure that combines precision and recall for both the ROG1 and ROG-L from the score dictionary. Now let's discuss counterfactual robustness. To calculate counterfactual robustness, the generated answer is compared with a counterfactual, that is contradictory answer, such that the robustness is measured by ensuring the two answers are different. Let's define a function named counterfactual robustness that takes two arguments, generated answer and counterfactual answer. Convert the generated answer and counterfactual answers string into a space-separated string of their characters. This step ensures that each character is treated individually for comparison purposes. The use of join method in the space essentially reconstructs the input string by adding space between each character. Finally, it returns a Boolean value indicating whether the generated answer is different from the counterfactual answer. This Boolean value, that is true or false, represent the robustness of the system. If the generated answer differs from the counterfactual answer, the function returns true, indicating that the system correctly handled the contradictory query. Now coming to the negative rejection, it is the ability to reject inappropriate queries, which is measured by checking for the presence of negative keywords in the generated answer. Let's define a function as negative rejection that takes one argument generated answer. We will use our helper function that is to convert it to list to split the generated answer into our individual characters of words. The resulting list is then joined into a single string with the spaces between each character or word to ensure that the answer is in consistent format for further processing. Now let's define a list of negative keywords that indicate a negative or inappropriate response. This keyword will be used to check if the generated answer containing any negative phrases. Finally, returns a Boolean value indicating whether any of the negative keywords are present in the generated answer. We will use lower method to ensure case insensitive matching, and the any function checks if any of the negative keywords are found in the generated answer and returns true or false. Last but not the least is latency. To calculate latency, measure the response time from receiving the query to delivering the answer. The time taken for the entire RAG pipeline to process the query and generate a response is recorded. Let's define a function named measure latency that takes two arguments, query and RAG pipeline. This query is expected to be a string representing the user's query, and RAG pipeline is expected to be a function or method that processes the query and generates a response. Now, let's record the current time in seconds and stores it in a variable start time. This marks the start time of the query processing. Now call the RAG pipeline function with the query as an argument and store the generated response in the variable response. This line represents the core processing of the query by the system. Now record the current time again and store it in a variable called end time. This marks the end time of the query processing. It calculates the latency by subtracting the start time from the end time. The result stored in the variable latency represents the total time taken into the process of the processing the query and generate a response. This is the main function that evaluates the chatbot's performance across multiple metrics. It takes four arguments: user query and ground truth, get response and vector store. It iterates through each query and its corresponding ground truth. It retrieves context from the vector store and generates answer using the provided get response function. And finally, calculates and stores the result for precision recall, relevance, entity recall, and all other metrics we discussed. The function returns a dictionary containing all the calculated metrics for further calculation and further analysis. Now let's see how to call the evaluate metrics function from our chatbot. So firstly, let's add a header to the sidebar of the Streamlit app, which is titled as a evaluate Mintra bot RAG pipeline. This helps in organizing the user interface. Using st.sidebar button to create an evaluate button in the sidebar. The code inside this if block will only execute when the button is clicked. So now define a list called queries. Here I'm providing a single query that is a user query, and I'm writing as I want a sweatshirt for boy in a yellow color. Now let's define a ground truth. It contains context and answer. Context is a list of relevant product information related to the query. An answer is a string that provides a detailed description of the product that matches the query. This is the expected correct response for the query. Now call the evaluate metrics function with the queries, ground truths, the get response function, and vector store as an argument. This function calculates various performance metrics for the chatbot based on the provided user query and ground truth data. Now let's iterate over the calculated metrics for each metric. It writes the metric name and the average value of the metric to the sidebar. Let's run our code to evaluate performance metrics of the RAG chatbot. So firstly, generate vector embeddings and by running the Python vector embeddings.py command, and then run our chatbot using the Streamlit run mintrabot.py command. And this will open our application in the browser like this. So this will open our application in the browser like this. Let me write a query. I want a sweatshirt for a boy in a yellow color. Let's see what it will respond. So it has responded. Sure, I can help with that. Based on the Myntra product catalog, you might be interested in US Polo Kids Boy Yellow Hooded Sweatshirt by US Polo Kids. It's designed for boys, priced at 8.99 INR and is primarily yellow in color. This sweatshirt features a hood with drawstring fastening a full zip closer, a long sleeves with a applique detail, a split kangaroo pocket, and an embroidered applique on the back. It has provided a pretty good response. Now let's evaluate a RAG pipeline with this user query and this generated response. So here is the precision, recall, relevance, and all other scores are calculated. So the precision is 69%, that is good. Recall is 78%, relevance is 13, entity recall is 100%, and faithfulness score is 48%. BLU is 33, ROG1 and ROG-L score are 0.73 and 0.59. Latency is 0.24. Noise robustness and is 0.12, and counterfactual robustness is 1, and negative rejection is 0. If I have asked any question which is not relevant to this chatbot, for example, I have asked what is Python, so this negative rejection will come as 1. So it has the tendency to calculate this negative rejection as well. So these are the results which we have already seen. Now let's talk about some improvement strategies to improve our metrics. So by using an enhanced vector representation, it will upgrade the embedding model to capture the better semantic relationship, improving the quality of retrieved context, and the enhancement can be expected to increase the context relevance. and precision, recall, and leading to more accurate and useful responses. So, I will suggest to use this enhanced vector representation by upgrading the embedding model. Secondly, you can obtain context filtering, which we can apply by adding an additional layer or post retrieval using TF-IDF vectorization and cosine similarity to scores and select the most relevant context. Third, we can fine tune the LLM by fine tuning the large language model on a domain specific data set to improve the accuracy and reliability of a generated answer. And finally, we can apply a consistency checking mechanism to compare the generated answer with the retrieved context and ensure alignment. So this is it for today. Thank you for watching.